All right. We had a little break in the semester. I hope you guys enjoyed your one day off. And now we go straight through to the end of the semester. We are going to pick up where we left off in the last class. We were talking about um, instructions, MIPS instructions, and we talked about how to deal with a stack, why we need a stack, and how load word and store word instructions play along with stack and stack pointer. We're going to start today talking about addressing mode. What that means is when you're looking at operands, how do you address them? There are 5 different ways of addressing in MIPS. So we'll take a look at each of these, and some will go into some examples. So the first one is the immediate addressing mode, in which the operand is provided as part of the instruction in the immediate field, right? So this is an I-type instruction in which the first few bits are for the opcode, the next 2 are for the source registers, and there is a 16-bit immediate field. 16 bits that you could use to provide a signed constant as part of the instruction. So for example, we have here an add immediate instruction in which we are taking the current contents of T0 register, adding 100 to it, and then we are storing that result back into the T0 register, which is a 32-bit register in the register file. Now, none of these are in the memory, so we wouldn't have to use load word or store word. Our constant is part of the instruction, and our operands are in the register file. So things are going to go pretty quickly here in terms of executing this particular instruction. So this is a mode of addressing in which the operand is provided in the directly in the as part of the instruction, right? So I can like write this operand is provided as part of the instruction. So this is your immediate addressing mode. The next one is a register addressing, which is essentially for the R-type instructions. Now, when I'm looking at an operand, where is it? Well, operand is a register. And the example over here is to add the contents of T0 to T1 and put the result back in T0. And clearly, the registers over here are where the operands are. So that's how we are addressing operands in the register addressing mode. And we have 2 different types of registers involved in R-type instructions. We have RS and RT. We have RS and RT as our source registers. In this case, those are going to map to T0 and T1. And we have the destination register, which is going to be T0 in this case. And then we have the shift amount and the function code that follows. But here we are addressing using the register itself. The next one is slightly different, and this applies for load word and store word instructions. Remember that these 2 instructions in MIPS are the only instructions you would use along with your memory, right? So whenever you want to bring some things from memory into the register file or put things back into the memory from the register file, that's when you would be using load word or store word. Now for this is going to be another I-type instruction in which we are going to use a different mode. Here it is going to be the base addressing mode. So essentially the difference between base addressing and your immediate addressing is that the 16-bit field that was there is now going to function as a base address. Earlier it was being used for a immediate constant. So what do we do with this? So suppose we have an address, the base address over here, we are going to put an offset into a register in the register file. So this is where our offset goes, right? This is our base register here and base address here. Oh, no, 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 no. So we are going to take the base address goes into the register. This is going to be our offset address. And this is where our base address goes, right? Because look at the example over here at the bottom for load word. When we say load word, from where to where? Well, it has to end up in T0, but it has to come from a memory address that uses T1, the contents of T1 as our base address, and it adds a offset of 100 to it, right? Register, that's your base address. Let me color code this. Maybe yellow, blue I can use. That register is your base address. And that is here. And then the offset address, which is that address, the 16-bit, that's essentially your immediate constant. That's the only difference. And we take that offset, we take the base address, add them up, and then we are going to use that to load a particular word from memory into one of the registers, in this case T0. Right? So this is another addressing scheme. Now, this particular diagram might be a little bit confusing. What are we trying to access? A byte, a half word, or a word? So our memory, right, no matter how wide it is, right now we are looking at accessing a word, but remember it is byte addressable, right? So it's essentially pointing to a particular byte which belongs to a particular half word, which belongs to a word, right? So a word is 32 bits, half a word is 16 bits, and half of that would be 8 bits. So this particular diagram is essentially showing that you are using all of this to pick out or to address a particular byte, because MIPS load word and store word instructions are byte addressable, right? So we are trying to address a byte which belongs to a particular half word, which belongs to a complete word, right? All right, so that's where our operand is, right? That's what we are loading. Operand is in the memory, and we are essentially providing the address to that memory location using two things. One is the register, and one is the immediate constant. The register is giving us the base address, which is sort of part of the register file, and then the immediate constant as your 16-bit address here. All right. The next addressing scheme is PC relative. So this is program counter relative. So essentially, can we move the program counter relative to the current program counter up or down by using this particular addressing scheme, which applies for branch instructions, right? Whenever you're doing a branch to a certain location, you are branching off of your current location, which is your current program counter. So what would you need? Well, you still have for branch instructions an I-type format, operand, source registers, and an address. But because this is PC relative, what you do is you take the value program counter plus 4, which essentially is pointing to the next instruction. You add that to your base address, which is over here, right? So you are going to provide this in remember from the previous class, this field is provided in words, not bytes, right? So if this guy is 2, that means we are offsetting by 8 bytes, because this is in words. But whatever that is, we are going to add that to our current program counter plus 4, and that's where we are going to jump, right? So this guy is going to be a 16-bit signed number in words. We are going to add that to PC plus 4, and when we do that, we get a memory location which is byte addressable. So we get a 32-bit unsigned result which can be used to access that particular location in memory, right? Which is often used in branching instructions, whether it is checking for equality or not equal. So that's relative to the program counter. Now, in terms of alignment, there are two things that could happen. You can look at alignment as far as programs are concerned, which are a set of instructions, or you could look at alignment just in terms of data. So when we are looking at data, then it can be very arbitrary, right? So you can have, it doesn't have to be word aligned. These can be arbitrary byte addresses, and we can do a byte addressing scheme to access particular data. So for example, if you wanted to get a particular byte out of a word, you could do that for data, but not for programs, because we know that instructions are 32 bits each in MIPS. We are going to make sure that the instructions which make up a program are word addressable and they are aligned word by word, right? In this case, it has to be divisible by 4 because it's going to do 32 bits at a time. So in other words, data can be starting and ending within a word. However, for instructions, you start at the start of the word and you end at the end of the word. That will make up your 32 bits. So let's take a look at an example here, which is for the PC relative addressing mode. So the address that we provided was a word offset and not the byte offset. Quick question, you guys. This one is in words, right? If this was load word and store word, what would be this address? It would be the offset address, which we are trying to add, is going to be a multiple of 4 in that case. You guys remember that? And then we are trying to access a byte. But for branch instructions, we say, all right, it has to be in words, because when you branch to an instruction, and that instruction is word aligned. So let's come back to this and say, all right, yeah, so it's a word offset with respect to the next instruction, not the current instruction, which is why we see a PC plus 4 over here and not PC. In other words, if you are not branching, then this address would effectively be 0, and you would start working on PC plus 4 if you were not branching. All right, let's come back here. Okay, so if you have a word offset that you can provide using a 16-bit field, a 16-bit field, a signed 16-bit field gives me the range of negative 2 raised to 15 to positive 2 raised to 15 minus 1. But because each word is 2 bytes, I can use this PC relative addressing scheme to branch to 2 raised to 17 bytes up or down relative to the program counter. And most branches are actually local, which is why this works very well, right? So principle of locality is a concept that we are going to learn later when we go into a discussion on memory, which is very detailed. But essentially that means that principle of locality essentially means that if you are trying to read some things, then you tend to read things that are local to the current address in memory, as opposed to making big jumps away from that. So whenever you're trying to read or write to memory, more often than not, you tend to do that very, very close to memory addresses. You don't do address 1 and then address 1000 and address 10,000. You don't go big jumps. You go sequentially many times. So that's essentially your principle of locality. So this works very well, right? Because branches now have something relative to PC, either above that memory address or below that memory address, but it is going to be essentially local or relative to the program counter. So most branches we would be okay with. So let's take a look at this example. We have the instruction itself in assembly provided over here, and that instruction is written at this particular address, right? So the address currently is, the program counter currently is 80016, and that particular address is given in decimal number system. So this particular address location has this in assembly, which is compare the contents of register T0 and S5, and if they are not equal, you jump to this new address which is labeled as exit. So the question is, how would I write the code for this using our I-type instruction, right? So clearly for branch when not equal has an opcode, which is 5. So that goes over there. That's not going to be a problem. The next two, the registers that we are comparing are T0 and S5. Those are going to be referenced as RS and RT, and you can look up those register numbers and they will be 8 and 21. So those go over there as a 5-bit number. And the last one over here is exit, which is being provided using a word offset of 2, right? So that, if I can highlight that, so that address is essentially being referenced using 2. So what does that mean? What does 2 mean? Is it going to address 2? What is it doing? Well, take a look. Program counter is right now at 80016. What would be the next value here? Well, the next instruction would be 80020, right? Because we are going to add 4 bytes to get to the next word, and programs are word aligned. So the next one is going to be at 80020 in decimal. That's PC plus 4. I have a word offset of 2, which means that I'm going to add the word offset to my PC plus 4 because this is the PC relative scheme. But 2 words cannot be just added directly. I need to convert that into bytes. So 2 words effectively is 8 bytes. So I'm going to add that to my PC plus 4. I'm going to get my branch destination as 80028, and that's exactly where I would jump. So this label of exit essentially is referring to an address in memory which we computed as 80028, given this is 2 words, right? So, there is nothing in memory called exit. Exit is just something that we are using as a label to point to 80028, where you will have a different instruction written up, right? So you will have maybe add I, some instruction written up over there. So when it branches to that location of exit, which is that memory location, it will start executing this add I instruction there. So I hope that that example gives you a good idea about how to use that immediate field in branch to provide a word and then translate it to a branch destination. Now, the last type of addressing mode that we are going to talk about is a pseudo-direct addressing scheme that applies for the 2 J-type instructions. Those 2 can anybody tell me what are the 2 J-type instructions? There are 2 J-type instructions with opcode 2 and opcode 3. You guys remember that? Jump and link, right? Jump and link has an opcode of 3. And what is the other one? Jump, right? So there is jump, and then there is jump and link. Jump and link is essentially used to store the return address, right? So to link up to the return address, so that we know after you jump where should you come back after your procedure gets done. All right. So in this particular J-type instructions, you only have 2 things. One is a J, the opcode to indicate that it is a J-type. And then it is followed by a 26-bit word address. But, clearly we are addressing things using 32 bits. So how am I going to construct a 32-bit address when only 26-bit are given to me? Well, the way you do it is, first you can translate a 26-bit word into a 28-bit byte address. Anybody tell me how am I going to accomplish that? How do I go from here to here? make a 26-bit word, add 2 zeros to the end. Perfect. Or can I say shift left 2 bits, and the empty spots it creates, I'm going to add 2 zeros to the end, right? I'm going to do shift left 2 places, and the 2 empty spots it creates, I'm going to fill in 2 zeros over there. I got a 28-bit byte address now. Now, using this 28-bit address, I still need 4 more bits. So I'm going to jump relative to my program counter. But the difference between PC relative and pseudo direct is that when you are using this for PC relative in the branch instructions, that range is very limited, right? It is basically limited by those 16 bits that we are using for word offset. But over here we have 28-bit byte address, so only 4 bits we can get from the current program counter, right? So that's a pretty big jump that you can consider, but it is still technically relative to the program counter. So you look at the current program counter, then you steal the first 4 bits of the current program counter and append them to this 28-bit byte address. That's how you are going to get a 32-bit jump destination. 4 bits from the current program counter, 26-bit words translated into 28 bits by shifting, adding 2 zeros to the end. That's how you constitute a 32-bit jump destination. All right, so because now we have 28 bits, that is going to essentially limit our range over which we can jump. Because 28, we are going to have 2 raised to 28 addresses over which we can make that jump. So that's a 256 million addresses for which we can over which we can make that jump relative to the program counter. So the upper 4 bits of the program counter are retained, and this actually avoids jumping across those 256 megabyte boundaries in the memory. So a longer jump, but still technically relative to the program counter. All right, so this completes our discussion on addressing modes that we had left off from the previous class. Now let's come back to our normal schedule, which is to talk about arithmetic for computers. Why is the range 28 to 28 with always 2 zeros at the end? So we are looking at bits, right? Let's see. We are looking at bits. Where is it? Right here. So I said megabyte, right? So I didn't say megabit. So if I'm looking at bytes and I want to find how many byte addresses over which I can jump, I need to consider 28, right? In other words, if you were asked how many words would you be, what would be the range in terms of words, then you would not use 28, you will actually use 26, right? All right, let's go back. Now, today we are going to be talking about arithmetic for computers. So when you're talking about arithmetic for computers, we are going to look at the multiplication operation and the division operation, and how do those operations get carried out by computer hardware. That's essentially what we are going to focus on for today. But before that, we also need to have a sort of a quick refresher on how do we deal with signed and unsigned numbers. So do we use signed magnitude? Do we use 2's complement? What do we do? So if you look at just signed numbers, bits are not going to have any, bits have no inherent meaning, right? So if you are given a 32-bit sequence, well, you don't know what that is for, right? It could be interpreted as a signed number, it could be interpreted as an unsigned number, it could be represented as an instruction, it could be represented as a floating point number. So a lot of options here, right? So without context, bits don't mean anything. So what are the problems here? We need to be clear about how are we representing signed numbers. Finite number of bits, because when we are doing arithmetic, 32 bits getting added to 32 bits and the result is 32 bits, then overflow can occur. So we may have to have certain flags in the hardware to monitor such things happening, because we have finite number of bits. And another complication is, okay, if we use a particular scheme for signed integers, how are we going to represent fractions and real numbers? How are we going to represent very small numbers to very large numbers? How are we going to represent floating point versus fixed point numbers? So all of that is something that we need to be explicit about, because just giving 32 bits is not going to cut it. Now let's take a look at the two famous signed representations that you guys have seen in your previous courses. The one on the left is okay, it's easy to understand, but it doesn't work for arithmetic because it requires more hardware, right? Essentially, it requires a comparator, which is a complicated piece of hardware which is not used in 2's complement arithmetic. So how does it work? Well, let's take an example over here. The one that we are playing with over here is a 3-bit example, right? 3 bits we are using. And this is signed integers we are looking at. So clearly we are going to have to reserve 1 bit for sign, and we reserve the first bit or the most significant bit for sign in both cases, right? In both the sign magnitude as well as for 2's complement, we reserve the most significant bit for sign. So half of them are positive, half of them are negative, roughly, right? Not always, because you see this, if you had 0, 0, 0 for plus 0, 1, 0, 0 is also minus 0, which essentially are the same number. So, roughly half of them are positive, half of them are negative. Well, if the first 2 bits are for sign, the first bit is for sign in both cases, what about the next 2 bits? Well, for the sign magnitude case, it was pretty simple, right? Because we just took the next 2 bits and we said, that's my value. 0, 0 is 0, 0, 1 is 1, and so on, right? So we literally separated out the sign and the magnitude. It worked very well to represent numbers, pretty simple. However, the problem here is that when you end up doing arithmetic with sign magnitude, you will get into a lot of complications. Think about how are you going to add things, how are you going to subtract things. You are going to end up with needing a comparator. So we move away from that and you look into 2's complement, which works very well for addition, subtraction. You can use the same hardware no matter what operation you are trying to do, addition versus subtraction, right? So which is why it makes it a lot more attractive, and that's what we are going to use for arithmetic even in our course. And that's what we use. That's the popular scheme to represent signed numbers. Next, the next 2 bits, how are you going to find the value? You guys remember that? Let's take some number here just to do an example, and this should essentially work as a refresher here. So if I took this guy as an example, 110, this actually doesn't work that well. So let me take another example. Let me take this guy. Right, 111 is -1. How do I know? Well, the first bit is 1, so that's negative. The next 2 bits are 1, 1. So in order to find the value of the number, I'm going to flip all the bits, which will give me 0, 0, 0, and then add 1 to it, which will give me 1, right? So 0, 0, 1. So I had found the sign already. Now I found the value of the number, and that's how I get -1, right? Flip all the bits and add 1. So you guys, I'm pretty sure you guys remember that from before. All right, so that's a quick refresher on 2's complement and sign magnitude, why sign magnitude is not going to work well, and why we need to be looking at 2's complement arithmetic in detail. But in both cases, one thing is crucial: number of bits, right? Because number of bits, only when that is explicitly mentioned, only then we can talk about making the first bit or the most significant bit dedicated for sign, and all the others related to the magnitude. All right, next we talk about negation and extension. So when I think about extension, I think about avoiding situations with overflow can occur, right? So for example, if you're trying to multiply two numbers, you know that multiplication is successive addition, right? So you're adding many times, and that's essentially what multiplication is. Well, if you're adding many times, what if any one of those additions you have an overflow? Well, clearly overflow means invalid result. So if you are adding two numbers multiple times during a multiplication operation, you don't want to deal with invalid result. You want to have a valid result. So what you can do is you can do a Sine extension every time you multiply, every time you add, sorry, and every time you add, you extend it by one bit. And when you do that, you avoid any chances of overflow. That's called a Sine extension scheme, right? That's a scheme that you can use to extend bits. One bit would be enough to avoid overflow when adding two numbers, but that's what we are going to look at. So to negate a 2's complement number, what do? You complement all the bits and you add 1. How about extension? To extend the number of bits in 2's complement, you essentially copy the most significant bit, which is your sign bit, into the higher bits. For example, here you have two cases. The first case is a positive number. The second case is a negative number. I know that by looking at the sign bit. For the positive number, the Sine extension, remember it as Sine extension, that's probably going to be a lot easier. So what do? Well, if you want to extend the sign, you can have, this is the number, and if you put one more zero up front, you have extended the number of bits from 4 to 5. So you have added one more bit, but you did not change the value of the number, right? It is still 00010, which is still 2. And no matter how many zeros you add to the left, the value will still be the same, plus 2, right? So all you need to add to avoid an overflow is just one bit. But if you are talking about extension, you can add the sign bits to the left of the number as many number of times you want without changing the value. So you might ask yourself, when is that situation ever going to come when I'm going to need to extend a 4-bit number to 6 bits or 7 bits? Well, think about this. When you're doing a add immediate, right, which is a 16-bit add immediate instruction, has what? It has a 16-bit immediate field. That 16-bit immediate field is a signed constant. So if it's a signed constant, let's say we are representing using a 16-bit 2's complement number, that number, if it only requires 4 bits, but you have a 16-bit field to fill up, you are going to do a Sine extension, right? You're not going to, you're simply going to append the sign bits in front of it to make it into 16 bits. That's where this comes in. All right. So that's for the positive number. How about for the negative number? Well, for the negative number, the most significant bit is 1. Now, if you wanted to make a 4-bit number into an 8-bit number, all you do is add ones, extend sign, right? And the concept is the same. If you have a specific bit field to fill up, for example, the 16-bit field that we were filling up in the immediate instructions, we would need to translate our number into that 16-bit field. And we can only do that without changing the value, and the way we do that is using Sine extension. All right. MIPS 16-bit immediate is extended to 32 bits for arithmetic, right? So when you do the 16-bit immediate, when you are actually going to do the instruction like execution, right, in the ALU, that is also extended to 32 bits because the ALU is 32 bits. And it's going to be different for unsigned versus signed instructions. So sometimes you have instructions that operate in the unsigned world. For example, you had what? Add U, right? Add unsigned versus add. Or over here we have load byte unsigned and load byte instructions. So you will have to deal with unsigned versus signed, and the reason why we need to talk about that is because we claimed that bits have no meaning without context. And if you look at the instruction or the unsigned instruction, what kind of instruction is it? Is it unsigned? Is it signed? We need to have those bits we need to have separate instructions so that we have a unique opcode for unsigned versus signed instructions. All right. Overflow. How to detect it? How to handle it? How do you detect it? Well, it depends on the arithmetic operations, right? So if you are doing, say, 2C arithmetic, how would you detect it? 2C arithmetic. The easiest way to detect it is if you had a positive number added to a positive number and you got a negative result, that is a quick check whether overflow occurred or not. And there are many other ways that you guys looked at in COCO, for example. The two most significant carries are different or same, or if you just want to look at the range of the result, if the answer of your arithmetic falls outside the range of numbers that can be represented in the given number of bits, then overflow has occurred. So there are different ways of detecting overflow, looking at carries, looking at the most significant bits of the operands and the answer. But over here, I'm just describing one of them, which is very, very straightforward. To look at the most significant bit of the operands and the most significant bit of the answer. Positive, positive, it is negative, overflow has occurred. And negative, negative, you add them up and you got a positive result, overflow has occurred. Right? So that's how you would detect overflow, by monitoring certain bits of the operands and the result. How do you handle it? Well, a general way of a very common way to handle an overflow is to jump to an exception handler program. So there is an exception program counter, EPC, exception program counter, which exception that can be used to jump from any instruction while you are executing that instruction. Suppose you have an overflow. The moment overflow happens, that starts off an exception, which is essentially going to update the program counter with the address given in the exception program counter. So it jumps to a separate routine in the memory and starts executing instructions over there. That's one way of dealing with an overflow condition. Or wherever you get interrupted because of overflow, that address is saved for possible resumption. Or in many cases, you simply ignore overflow, right? So, for example, in 2's complement arithmetic, if you just want to keep doing the arithmetic irrespective of the overflow, I don't really care about whether overflow occurs or not. I just need to go through these instructions. That is one strategy, one way of dealing with overflow. So in that case, you are simply ignoring it. Separate instructions, like I said, for add u and add. Well, for add u and add, the difference is one is unsigned and the other is signed. When it is unsigned, then there's no particular restriction on the number of bits, right? The number of bits conversation starts making a lot more sense, and it actually holds value when you're looking at signed instructions, add, right? So in one case, the overflow is not really monitored, and in the other case, it is monitored, right? So it differs how we overflow is handled based on the instruction itself. Add u, it's an unsigned, don't really care about overflow. Add, it's a signed instruction, I do care about the overflow because I have a limitation on the number of bits for the operands, and for the instruction, I have specific places to look at sign, and for the rest of the bits to look for the magnitude of the result. Now let's get into multiplication. A quick recap of how you do multiplication. Well, in decimal, it's going to be pretty straightforward, right? If you treat 11 and 5 as decimal numbers and you multiply them, your result is in decimal. Now, what if I try to look at multiplication in binary, right? So suppose I represent 11 using 4 bits and 5 using 4 bits. And I would get a result, in this case 55, which is represented by more than 4 bits. In this case, I have 6 bits. But if you actually look at the worst case scenario, when I say worst case scenario, I'm talking about the most number of bits I would need to represent the answer of the multiplication. I would actually go 15 times 15, right? 1111 times 1111, I get 225, which is actually that 11100001, which essentially means 4 plus 4, right? So your answer could go up to 8 bits. How is that useful? Well, think about adding a 32-bit number, multiplying a 32-bit number to another 32-bit number. What are you going to get? You are going to get a 64-bit answer at the max. So you need to have registers that can be used to store the 64-bit result of that multiplication, and they are. There is a high register and there is a low register. The high register is often used to store the most significant 32 bits of the result of a multiplication operation, and low register for storing the 32-bit least significant bits of the multiplication operation. But the point is, your final register, your product register, is going to be double the size of the registers that you need to store the multiplicand and the multiplier. That's one. Now let's take a look at the multiplication in binary. How does that play out? And this should look very similar to how you would do multiplication in decimal, right? So suppose you lay out the numbers. Over here at the top you have 11 and over here you have 5. You're trying to multiply them. You have arranged them nicely, one number below the other. The top number you're calling the multiplicand, the bottom number the multiplier. Multiplication is commutative, so if you switch it around, it doesn't really matter to the result. But in this case, you are considering the top one to be multiplicand, second one to be multiplier. So what do? Well, you start off with, say, the least significant bit of the multiplier, right? So let me highlight that in blue. All right. The moment it is 1, if you see that to be a 1, you don't need to actually carry out the multiplication. You can simply take the multiplicand and put it under over here. Don't need to do anything. Don't need to change it. Just copy it over. And once you are done with the least significant bit, what do? You move on to the next bit. But before you actually move on to the next bit, you actually shift left, right? Over here, you can see you have shifted left one place so as to look at the next most significant bit of the result, right? Because this already gave you the least significant bit of the result. Okay, so there is a shift left operation that's going on, right? Over here. Shift left by 1 bit. All right, so we are gonna, when you guys look at the algorithm, the flowchart, you will try to relate that back to this. Okay, so next, what happens? All right, you take a look at the next bit. What do we have here? The next one is a 0. The moment you see a 0, what do? Nothing. You don't need to do anything. You actually don't need to do the addition in this case. All you need to do is shift left 1 bit more when it is a 0. What do you do next? Well, you look at the next bit in the multiplier, next most significant bit in the multiplier. In this case, it is 1. What do I need to do? Just copy over the multiplicand. Move one place up, look at the last bit, most significant bit of the multiplier is a 0. Just move one bit to the left. Don't need to do the addition. And once you do all of that, you add things up, right? All of them, add, you get your overall answer. And this matches 55 in decimal. So what did we learn here? When you're trying to do multiplication in binary, your intermediate or partial products that you get are either going to be copies of the multiplicand or they are going to be zeros. That's it. And when as you are moving through the multiplier, you start all the way to the right, the least significant, then you move left, then you move left, then you move left. And as you are computing the partial products, you also are moving left one bit at a time as you are going through the bits, number of bits in the multiplier. So keep that in mind as we go and take a look at the flowchart here. So hopefully you can relate this flowchart back to the process of multiplication by hand that we talked about. The first thing that you do after you start is to look at the least significant bit of the multiplier. Let me point that out. Multiplier 0 is essentially looking at the LSB of multiplier. And clearly we are in the binary world, so this can either be a 0 or it can be a 1. So if it's a 0, what did we say? We don't need to do any addition, we just need to shift, right? When it is a 0, we just shift. Okay, so what are we shifting? We are shifting the multiplicand register left by 1. Okay, so that means I am placing my operands in registers. Alright, so what all do I need? Let's see. I need a register for multiplier, multiplicand. What else? The product, the answer. Right, so I need all these. And if I say my multiplier needs to be 32 bits and my multiplicand needs to be 32 bits, then my product register needs to be 64 bits. Okay, so I have a register for multiplier, multiplicand, and a product. All right, so what next? If it is 0, I don't need to do any addition, which I would need to do if that multiplier least significant bit would have been 1. But in any case, the next thing that I will do is shift the multiplicand register left by 1. Why am I doing that? Because no matter what I do, when I multiply with a 1 or multiply with a 0, no matter which one it is, I move left. I move left 1 bit. That's what I'm doing here. Shift the multiplicand register left by 1 bit. Now let's take a look at what should I do when the multiplier least significant bit is 1. Well, when the least significant bit is 1, what do? Oh, it looks like I need to take the multiplicand and add it to my product register. So if I initialize my product register to be all zeros, then every time I come across a least significant bit of that multiplier to be a 1, then I need to add the multiplicand to the project register and place the result back into the project register. So initialize with 0. If the least significant bit is 1, then you add multiplicand to the product and then place the product back into the product register. So this is like saying I added this, shifted, added this again to what? To the product register, which started at all zeros. Right, so this is your product register. In other words, all you needed in this case was add 1 0 1 1, move left, add 1 0, move 2 left. So 1 2 1 1 0 0. That's it. All you did was this. This added to that, and you got your answer. Right? Let's take a look. So you add when you have that as 1. You don't add when it is a 0. You just shift. So the second step in this multiplication procedure was what? Shift the multiplicand register left by 1 bit. What does that mean? That means that as you are moving this left, you are essentially moving this guy left, 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 right? Because if there is a 1 at a higher place in the multiplier, you would need to move things left first and then add it to the product register. Okay. But I also need to adjust my multiplier, right? Because every time I exhaust the least significant bit, I need to drop it so that I can start looking at the next most significant bit in my multiplier. So what I'm going to do is, I'm essentially going to shift the multiplier register right by 1 bit. So essentially what that means is, if I move this guy to the right and I kill this least significant bit, this becomes my new least significant bit. After that, this becomes my new least significant bit. After that, this becomes my new least significant bit. So that is accomplished by a shift right by 1 bit operation for the multiplier register. And I need to do this 32 times to complete a 32-bit multiplication process. And once I reach that 32, if that number is 32, then I'm done. If not, I go back and check my least significant bit of the multiplier. All right, I'll take a moment here to take your questions regarding this. So if you understand this flowchart, then when you look at the block diagram to represent the hardware for a multiplier, things will be pretty straightforward because there will be a one-to-one mapping of this. Can you go over how each bit of the product is found? So the product register starts off with an initial value of 0, right? So for example, if you are doing a 32 and 32, right, 32 bit multiplied by 32 bit, your answer can be 64 bit. And if your answer is 64 bit, you would initialize them to all zeros first. Then you either add the multiplicand or you don't add the multiplicand to the product register. You add it when the least significant bit of the multiplier is 1. You don't add it when the least significant bit is 0. When you add, you are essentially changing, right? So let's suppose our product register in this case was 8-bit, right? So you're doing 4-bit multiplied by 4-bit to get 8 bits. So you would start off with 8 zeros in the product register. And the first time you look at this particular one, the least significant bit is 1, you would add the multiplicand to your product register and save it back into the product register. What that means is change this to 1011. That would be the current value of the product register to exhaust this particular one, to complete working on that one in the multiplier. Then what do? You move to the next one. You look at the next 0. When you take a look at that 0, what are you doing? Well, nothing. You don't need to add anything. You just shift the multiplicand, right? Shift the multiplicand. So it's right now going to be over here, right? 1101. But are you adding? No, you're not adding. When are you adding? When you shift it the next time. Because there is a 0, after that there's a 1. So when you shift it the next time, that's when you will add. When you add that, it'll look like something like this. All right, looks like you got that. Okay, let's go back to this. Other questions about the procedure? All right, so let's talk about the hardware. What do I need to do to accomplish this? What do I need to accomplish 1A? What hardware do I need to accomplish 1A? Add multiplicand, adder, okay. So I need ALU, right? Now, the question is, do I need a 32-bit ALU or do I need a 64-bit ALU? If I was multiplying 32 bits with 32 bits, question is, do I need a 64-bit ALU or a 32-bit ALU? Answer this by looking at this particular statement and what are the register involved. 64-bit, you are right. So I need a 64-bit ALU at least to begin our discussion. Maybe we can reduce it later on. I need a 64-bit register over here because one of the things that I need to add is a product register, and my product register is going to be 64-bit because my result can be 64-bit. So I need a ALU that can add 64-bit to another 64-bit number. Okay, so I need a 64-bit ALU for that. I need I need the multiplicand register to be shifting left, right? So this is what accomplished using a shift register. And in this case, this shift register is going to be used to store the multiplicand, and it has to have some control to move things left. Similarly, for the multiplier, I need a shift register which has the control. So the user or some control unit should be able to tell it to move right. That's it, right? I need something to shift left. I need something to shift right. I need some things that can do this check for the least significant bit of the multiplier and whether 32 repetitions have occurred or not. That's it. That's all I need. I also need the 64-bit product register. The other question that I want to ask is, soon after you start, what are you looking at? Are you looking at the multiplier? Are you looking at the multiplicand? And are you looking at the product? Which one are you looking at as soon as you start? Well, step 1 tells me that it is the multiplier, right? So when I start, my whole multiplication operation is going to be based off of values in the multiplier register, specifically the least significant bits in that multiplier register. Okay, I think we are ready to look at the hardware now. Now, hopefully when you look at this, all the things that we discussed earlier should map one to one. What do we have over here? We have a 32-bit multiplier register with the capability of shift right, which is controlled by this control unit over here, whether to shift right, when to shift right. There is a 64-bit multiplicand register. Do I need all the 64? No, I don't really need all the 64, but I'm doing a shift left. So if I have 32 bits over here and I'm shifting left, I need a place for them to go over here, over there, right? So what I'm going to do is, when I start things off, I'm going to put 32 bits of the multiplicand over here, and I'm going to fill all of these guys with zeros, 32 zeros, and I'm going to use those 64 bits going into the 64-bit ALU, which over here I'm only using to do a 64-bit addition. What do I do with the product register? Well, my product register is a 64-bit register which gets updated, right? So whenever I'm doing step 1A, what am I doing? I'm taking a look at the product register, adding the product register to multiplicand, and the result goes back into the product register. See that? ALU, multiplicand, current contents of product, added, goes back into the product register. All of this is being controlled by this control test block. Many of the things are outputs from this. So for example, if I use a yellow wire to indicate outputs, all of these are outputs. There is only one input in blue. Can you guys tell me what that blue line signifies? what particular thing is an input to this control test, based off of which all the other control signals are being sent. 32-bit exhausted. It's the least significant bit of the multiplier. Yes. So I'm looking at the least significant bit of the multiplier, and whether it is 0 or not, whether it is 0 or a 1, that becomes my trigger. That becomes my trigger whether to shift left, when to shift left, right? I shift left regardless. When to shift left, when to shift right, when to add, and when to rewrite the results of this addition into the product register. When it is 0, what do? I don't need to add, but I still need to do steps 2 and 3 when it is 0. So when it is 0, I still need to do shift right, still need to do shift left here, don't need to add, I don't need to write. I just need to do shifting. When it is 1, if I'm looking at it 1, need to do shift right, need to do shift left, need to add, and need to update the results in the product register. So need to write to the product register. Now, after everything gets done, what happens, right? This happens as this shift right operation is happening. You are going to look at the least significant bit and then bit, and so all the 32 bits of the multiplier are going to get looked at. Depending on whether they are a 0 or a 1, all the addition happens. And at the end, after that 32-bit cycle, you are going to get a 64-bit product into the product register. And that is your answer of the multiplication. Now, a couple of things that are bad in this case, right? Negatives or disadvantages of this hardware. Can you guys tell me what are the disadvantages that you see here? Do I really need a 64-bit multiplicand? I have a 32-bit number that I'm multiplying. I'm using a 64-bit multiplicand. So that's a problem, right? 32-bit multiplicand would have been okay. 32-bit ALU would have been okay, right? Because if I'm adding numbers only 32 bits at a time, I should have been fine. But I have a 64-bit ALU, so I would have wanted a 32-bit ALU, and I would have wanted a 32-bit multiplicand. Those are definitely two things I would have wanted. And maybe if there was a way to combine, instead of product, multiplicand, and multiplier, if I was, instead of 3 registers, if I was able to combine a couple of them into one, then that would have been really, really advantageous, because then I'm saving one register. Right? So let's keep those disadvantages in mind and try to improve our multiplication hardware. So here we have an improved hardware. This is the second version. We have a final version of this coming up as well. But the second version is, we observe that the multiplicand is not changing, right? The multiplicand always is the same. We are just shifting the multiplicand left one bit at a time. So how about, can we make do with a 32-bit register? That's our first question. Why do we need a 64-bit multiplicand? We're not changing the value. Let's try to use only 32-bit register for the multiplicand. Shift product right instead of shifting multiplicand left. So these are both the same, right? If I'm shifting the multiplicand to the left, that is the same as shifting the product register to the right. It is the same thing. This will allow us to use a 32-bit ALU and a 32-bit multiplicand register. So the improved hardware, and we are showing two things over here. One is the hardware block diagram and the flowchart for it. And nothing much changed over here. All that changed is 1A, right? We are still going through the start. We are looking at the least significant bit of the multiplier. And if it is 0, we are shifting that. When it is 1, we are doing that addition. But a few things changed. What? 1A and 2. Take a look at that. 1A became add multiplicand to the left half of the product, right? not right half or the whole entire product, only the left half. Add multiplicand to the left half of the product and place the result in the left half of the product register. So you're doing that addition 32 bits at a time as opposed to 64 bits at a time. And you're using only the left half of the product register as a placeholder for the answer. In 2, we are shifting the product register right by 1 instead of shifting the multiplicand register left by 1. Those are the only 2 changes that we have done. And look at this. Multiplier shift right capability 32 bits, exactly the same. Multiplicand now 32 bits. Okay, improvement. Now we need a 32-bit register as opposed to a 64-bit register. 32-bit ALU instead of a 64-bit ALU. But the usage of the product register has changed. Remember, earlier we did not have this shift right capability. Now, because we removed the shift left capability of multiplicand, we replace that with the shift right for the product. So the next question is, if the product register is shifting right, what is going to happen? Well, all of these are going to be moving to the right. The answer is 64 bits. So as it moves to the right, there are empty spots created over here, filled up with zeros, that can be filled in with our 32-bit addition that happens based on the least significant bit of the multiplier. Right? So this is like saying add, move right, accumulate. Add, move right, accumulate. Right? That's exactly how it's going to work. And at the end, what are you going to have? You are going to have a 64-bit result in the product register. You were able to accomplish that by simply using a 32-bit ALU and a 32-bit multiplicand register. So I hope that discussion. So are there any questions about the second version? You're still looking at least significant bit of the multiplier. All right. Now in the final version, the most improved hardware as far as multiplication is concerned, well, final version for the 32-bit multiplication is this. What we can do is we can use the product register. The lower half of the product register is going to have a wasted space. So what we can do is we can combine the multiplier and the product register. We can combine them. So the multiplier is consumed anyway, right? Because we are looking at the least significant bit of the multiplier and throwing it away. So because it is going to be thrown away anyway, what we are really interested in is the product register. So what we can do is we can split up that product register into a multiplier field and a product register field. We can initially put the multiplier in the lower 32 bits of the product register. And then as we are looking at the least significant bit of the multiplier, we can make our decisions. We can shift the product and multiplier to the right together, right? So essentially what this means is, if I go back to the second version, instead of starting everything as zeros and adding and putting the things over here and shifting, we can put the multiplier itself into the 32-bit field over here, because when you shift right, you are going to throw away that bit anyway. And instead of throwing out zeros, we can actually throw out the bits of the multiplier because they are anyways not useful after they have been consumed. So that is your final version of the multiplier shown over here. So now, instead of looking at the least significant bit of the multiplier, you are actually looking at the least significant bit of the product. Well, the least significant bit of the product is your multiplier, because the least 32 bits of the product register have been initialized with the 32-bit multiplier. And as you are shifting right, you are throwing away one bit of that multiplier that gets consumed. What is going to happen finally? Finally, what is going to happen is you are going to get the entire 64-bit product over here. Still using 32-bit ALU, 32-bit multiplicand, still using 32-bit ALU. So it's a similar to the second version, except for one difference, which is we are saving the 32-bit multiplier register and we are making that a part of the product register itself. Right? Earlier in the second version, we were filling it up with zeros and throwing zeros away. Now we are filling it up with a multiplier and making the decisions based off of that and throwing them away because we have consumed them already. All right. Now, all of that is fine as far as unsigned multiplication is concerned. But how do you deal with signed multiplication? Well, that's easy. You can just convert everything to a positive number, treat it as a unsigned multiplication, then have a separate circuit to keep track of sign of the product. So you multiply numbers as if they were unsigned. And at the end, you keep track of whether the numbers were positive or negative and adjust the sign of the result. So you could still use the multiplier. Now, before I move on to the next one, I want to ask you guys this. How many times do I need to use this 32-bit ALU? At the most, how many times do I need to use this 32-bit ALU? At the most. Assuming that everything, all the bits are 1, how many times do I need to add? Right, 32, right? Because if every bit is a 1, then I need to have 32 adders, right? It's like adding 32 addition operations. So I'm using the 32-bit ALU 32 times, assuming that I'm doing this step 1A when each bit is 1. That's the max, but I'm doing this addition 32 times. Well, if you had one instruction getting executed in one clock cycle, that would mean that I'm actually doing this for 32 cycles. And now if you expand this to 64, or if you go for 64-bit multiplier, you are going to have 64-bit additions that are going to slow the process down. So it looks like as you increase the number of bits, the time it takes for you to compute the multiplication result is going to linearly keep increasing. More and more addition operations. That's not very fast. So let's try to look at an alternative, which is the faster multiplier. And the difference is this. Instead of using one 32-bit ALU 32 times, let us just put all the 32 ALUs, adders, like let's use more hardware, use multiple adders only once, right? So you can either use one ALU multiple times, or if you had multiple ALUs, you just need to use them once, right? So by that, you don't have to wait. So this is a scheme to improve the performance, mainly the speed, but it will cost you because you will need multiple adders to do this. We are still multiplying a 32-bit number with a 32-bit number using 32-bit ALUs, 32-bit adders. And the way we are computing this 64-bit product shown at the end is, we are essentially doing a sort of a trickle-down product. So let's take a look. You start off with the multiplicand getting multiplied or bitwise ANDed with the multiplier, the least significant bit of the multiplier. So what does that give you? If you have a least significant bit of the multiplier, let me just identify this. This is LSB of multiplier, and this is the 32-bit multiplicand. You're doing a bitwise AND between them. Now, when you do a bitwise AND of this, what you get is a 32-bit number. And you are taking the least significant bit of that number and calling that your product 0, the least significant bit of the answer, which is sort of the same thing as saying, once I do, all the way back, once I do least significant bit of the multiplier multiplied by the multiplicand, you get what? You get 1011. The least significant bit of that result is actually the least significant bit of your answer. So you get your bit there, right? And then you move to the next one. Let me show you over here. The next most significant bit of the multiplier gets bitwise ANDed with the 32-bit multiplicand. And you get a 32-bit value over there. These two get added and a 32-bit result comes out over here. When that comes out over there, you can get the least significant bit of that result and get your product 1. And similarly, you can keep doing this, right? So what are you going to have? Well, in this case, you have a 32-bit field with 32-bit field, right? So you have your least significant bit of the multiplier, next one, next one, next one, so on, 28, 29, 30, and 31. So you've got 32 bits of the multiplier getting bitwise ANDed with all the 32 bits of the multiplicand. How many ALUs am I using in this level, in the blue level? How many ALUs am I going to have? You see this? 0, 1, 2, 3, 32. Am I going to have 32? 16, right? 16. Right? Because I'm doing 2 into 1, right? 2 into 1 and 2 into 1. Right. So 16 32-bit additions happen there. The results of those go down to the second level. Let's label that as the pink level. How many are you going to have over there? 8. Then you will have 4. Then you will have 2. Then you will have last one is your 1. And the way you get your result is least significant bit, so on up to 15th index. This 32-bit adder will give you bit 47 to 16, 32 of them, and then the next ones will give you all the way up to 63, making it a 64-bit product. Now, 2 questions we can ask here. How many adders do I need to complete this process? In total, how many adders did we have? In the first level, it looks like 16. Come on. 31. 16 plus 8 plus 4 plus 2 plus 1. Right? So, about the same number of adders that we had earlier, but now everything is happening in a parallel way, right? So earlier we used up 32 cycles to do that multiplication, to do that, 32-bit adding. We had to use 32 cycles, one for each iteration. How many cycles am I going to do? How many cycles do I need to do this? So ignore the time you would need to do this. If you ignore the time to do that ANDing at the top, how many cycles do you need to go through this entire chain? 5, right? 16, 8, 4, 2, and 1, right? 16, 8, 4, 2, and 1. Only 5 cycles I need to finish this, right? Which is what makes it faster. Now next, if I am if my current numbers that I'm multiplying are at the pink level, right? They are using the hardware that is on the pink level. Can I bring in new numbers to use the level before that? I don't know if you guys understood that question, but so let me try that again. Suppose I'm trying to add numbers A1 and B1, right? And those two are 32-bit numbers each, and they have already used this particular level, and they have gone down to this particular level. They have used the hardware before, and now they are using this particular level, the pink level. So the question is, can I bring in two new numbers, A2 and B2, start multiplying them, and start using the blue level? Can I do that? Absolutely. That is right. That is called pipelining. Several multiplications can be performed in parallel. So effectively, if you really look at this, even the 5 cycles will go down to 1 cycle, right? Because in every 1 cycle, you will get a new product out. You see that? So you can do this in 5 cycles, and you can use pipelining to reduce it to 1 cycle. Where is A2 and B2 going to write into their product 0 or product 1 in the pipeline case? So assuming that you are not like you are writing into a different location, right? So I'm just talking about the usage of the hardware, right? So suppose you would need to somehow another product register, yes, so you would need to figure that out on the other side. But just in terms of using the hardware, which is what makes things costly, right? If I have the hardware and it is not being used, I can use it to perform certain tasks. But I have to be careful. You're right. I need to be careful so as to not lose my product register itself. But pipelining can give you an additional boost in terms of making things fast. All right. Let's get into division. And things are going to be sort of exactly the opposite of multiplication, with a few changes over here. Instead of adding, we are now doing a successive subtraction, right? And when you're doing this division in hardware, you also have to be worried about checking for division by 0, right? So you would have to have some exception handler routine to figure out if you're trying to divide a number by 0, then that is invalid. You should not be able to move ahead with that instruction. So there has to be like some instruction that checks for 0 divisor. So let's suppose we are doing 1000, right? That's our divisor, and we are dividing 1001010. That's our number. You can start thinking of it as a decimal number divided by a decimal number to get a decimal quotient and a decimal remainder. Now, if those decimal numbers are restricted to only zeros and ones, then they translate into binary division directly. Because whenever you are trying to do this binary division, when you divide, your bits that you get for quotient has to be a 0 or has to be a 1, because you're dividing it by 2. So let's take a look at two approaches here. One is the long division approach, and the other one is the restoring division approach, which is much faster, and that's what we are going to do here. So the long division approach first checks for whether the divisor is less than or equal to the dividend or not. Where is the dividend? Dividend right here. Divisor right here, right? So first what do? You check whether dividend is greater or not than the divisor. Well, in this case, the dividend looks to be a lot greater than divisor. So what do? You put a 1 bit in the quotient if the divisor is small compared to the dividend, and then you do the subtraction of what and what. You subtract dividend minus divisor, and then you put the result. After you compute the result, you also bring down the next bit, right? 0-bit quotient. Otherwise, you would get a 0-bit quotient, and then you would bring down the next bit. And then what do? Suppose you are here. You have subtracted this by this. You got a 1. You brought down the next bit, 0. It looks like 1 0 is small compared to 1 0 0 0. So you bring in the next bit down. In order to do that, you add a 0 in your quotient. That is still not enough. So you bring in another bit, which in this case is your last bit, which is 0. All right. So that makes it another 0 because you brought down another bit. And at the end here, what do you have? 1 0 1 0. Yeah, that is greater than your divisor. So now you can put a 1 there in your quotient. Put the divisor down here. Subtract. You get your remainder. Right. So all of this requires what? Well, the first thing it requires is a comparison between the divisor and the dividend, right? Because it looks like you're doing this multiple times during a division operation. You see this? Divisor and dividend need to be compared. I need a comparator, more hardware, costly hardware. I cannot afford to do costly moves here. Instead, what I'm going to do is this. I'm going to perform this particular subtraction regardless of whether divisor is less than dividend or greater than dividend. I'm just going to do the subtraction. That is called the restoring division process. So do the subtraction, and if the remainder is negative, then you know that you did not have enough. So you add the divisor back. And when you do the subtraction and the remainder is positive, then it's okay. We can just put a 1 bit in the quotient and continue with our next subtraction operation. For sign division, just as in the case of sign multiplication, we did it for the absolute values, and then we adjust the sign of the quotient and the remainder as required. That's going to be later, based on the sign of the operands. In this case, an n-bit operand yields a n-bit quotient and remainder. And here is the flowchart, exactly the same way as we went through a flowchart for multiplier. Here is the flowchart for the division process. So first you start. The moment you start, you have a subtract the divisor register. Okay, so we need registers. All right, what are the registers we need? It looks like we need a register for the divisor. It looks like we need a register for the dividend. We need a register for the results now, quotient, and the remainder. Earlier we had multiplier, multiplicand, and product. Now we have 4 of them. 2 of them for the operands, 2 of them for the results. Okay, so now going back, subtract the divisor register from the remainder register and place the result in the remainder register. So remainder register is sort of functioning as our product register in the multiplication process that we looked at. But what does it have? Well, the remainder register, unlike the product register, right, you remember when we were talking about multiplication, we initialized the product register to be all zeros. Now we are going to initialize our remainder register as the dividend itself. Why? Well, just so that I don't have to use the dividend register. So I can strike this off and say remainder register is initialized uh, into dividend. All right, so subtract the divisor irrespective of how they compare. You simply subtract the divisor register from the remainder register and answer should be placed in the remainder register. Earlier we were doing addition, now we are doing subtraction. All right, once you subtract, you look at the remainder. The remainder, depending on how they compare, could be greater than or equal to 0 or it could be less than 0. We said if it is less than 0, we need to do the restoring. If it is greater than 0, what do? You shift the quotient register to the left, setting the new rightmost bit to 1. So the quotient register is moving to the left. You can initialize it to be all zeros. You move things to the left and the new place it creates, you can fill up with a 1. If it was less than 0, then you perform 2b, which is I did not consume my divisor in my dividend. So restore the original value by adding the divisor register to the remainder register and placing the sum in the remaining register. So whatever you subtracted earlier, you undo that by adding the divisor back into the remainder register. Answer goes back into the remainder register. In other words, 2b goes back to whatever you had before step 1 was completed, right? But also you need to shift the quotient register to left, setting the newly significant bit to 1. Did not get consumed, quotient should become 0. That bit should become 0. The new bit it creates, because when you move things to the left, it creates an empty slot. That slot fills with 0 here and it fills with 1 over there. After you are done with 2a and 2b, depending on which path you are on, you shift the divisor register right by 1 and you repeat this exercise 33 times. That's essentially going to be your division, sort of the flow chart for the division process. Let's take a look at how does the division hardware look like. Again, we are doing things in a not so efficient manner first, and then we will try to do it in a slightly more improved manner. So we have a divisor here which is 64 bits. Initially, divisor in the left half. Divisor is in the 32 bits over here. These are all going to be zeros. Quotient register is a 32-bit register which we will be able to shift left. When we do shift left, we either put a 0 or a 1 depending on that comparison. Right? We look at the remainder. If it is positive or negative, we shift left quotient, filling it by a 0 or a 1. Filling that empty spot with a 0 or 1. Okay. And because this is a 64-bit divisor field, bunch of them are zeros, but it is a 64-bit divisor. The remainder is 64-bit. We need to subtract them using a 64-bit ALU. The answer of that is going to be a 64-bit field that goes back into the remainder. So what are we doing this using this control? We are only observing one thing, which is the answer of the subtraction, right? So when you subtract, you go into that remainder, you may write to it or you may not write to it, but that's exactly what you are observing. Let's see, where is that? Now let's take a look at what it is controlling in yellow. You need to move things left and pad it with either the 0 or the 1, depending on whether you're doing 2a or 2b. For the divisor, you need to move things right. And as you are moving things right, those zeros will start creeping in and you will be losing the bits over here. you need to send the signal to do the subtraction. And if you need to do the subtraction to replace the results of the remainder, then you need to be able to write, enable, essentially enabling the write for the remainder register. So 64 bits for divisor, ALU, and remainder, 32 bits for the quotient. And like I said, the remainder register is initially your dividend, right? So you're essentially removing things from the dividend many times. And as you are doing that, you are looking at the remainder being positive or negative. If it is positive, you are filling the quotient with a 1, moving things left and filling it the empty slot by 1. If it is less than 0, you are moving it left and filling it with a 0. But now we are looking at the sign of the remainder. Earlier we were looking at the least significant bit of the multiplier. Now this is your optimized divider. Things are very similar in this case. The remainder register is now 64 bits with the right half having the quotient. Right? The right half of the remainder register is being used as quotient, and that is getting shifted right and thrown away to make at the end your remainder as your 64-bit result. This one is 32-bit ALU, the divisor is 32 bits. So you as we went from a non-optimized multiplier to an optimized multiplier, we are going from a non-optimized divisor to an optimized divisor. In this, the benefit is 32-bit divisor instead of 64-bit divisor. No need of a separate quotient register because it is part of the remainder register itself. And 32-bit ALU instead of a 64-bit ALU. So this looks a lot like the multiplier itself, except that the operations are different, which essentially means same hardware, different operations. So the control unit could use the same hardware as long as it is supposed to send those appropriate control signals to that particular hardware. So same hardware can be used for both. All right, so that completes our discussion. Activity 7 time. I'm gonna stop recording first.